Okay, so as Professor Lim mentioned, I'm coming to give a guest lecture today. But the kind of key idea behind this is it's not just teaching you about some concepts. You've kind of got a good foundation. But this is actually more of a research talk. So it's trying to show you, here's an example of how we actually apply these methods, like designing experiments, statistical analysis, in an actual conducting research out in the real world. And so the topic of this is actually going to be in how do we sort of build systems that perpetually enhance human learning through collaborative experiments, through making experiments dynamic and making them personalized. Let me, I think it's not quite showing up, 1 second. Great, yep. And so I'm gonna basically give this like a research talk. So give you a general introduction to the problem I'm trying to solve, the approach I take, and then several examples of experiments that use these statistics that you guys have used before. And if any of you are interested in these topics or in potentially doing research or volunteering, feel free to let me know. Okay. So I'm excited about the promise of software to enhance learning. Oh, this is an amazing projector. It's almost like it has a life of its own. Okay. So you might have heard of things like MOOCs or massive open online courses. Put your hand up if you've heard of MOOCs. Okay. So MOOC is a massive open online course. If you Google edX, it'll provide you free courses that anyone can learn from. You all might not care because you're paying for courses right now, but once you leave university, you'll be very happy for this. So you've got these online courses where anyone can learn anything they need for their career. What it means is that people can show up and just solve a problem. Type in answers, get feedback on what they're learning. These kind of technologies can also be used in on-campus courses. For example, you all use IVLE. What if we give you quizzes that could actually help you practice your knowledge? I'm also interested in how software can help people learn outside of formal education. So if you think about mental and physical health, many people struggle with issues like depression or anxiety. Smoking. Well, how do we help people solve these issues? Cognitive behavior therapy is a leading clinical method that's so useful that in the UK, United Kingdom, you can actually be written a prescription to do online cognitive behavior therapy because it has such a big impact on depression. And so one thing I've also worked on is how do we actually help people deal with depression? By teaching them cognitive behavior therapy. So you can see that effectively having software that helps you learn can help you with everything from your career to actually mental health. But we have a problem. Even when people provide these online resources, they're really never good enough. There's a lot of evidence that some problems just don't help students learn. They can attempt it over and over without gaining knowledge. And that often there are many apps out there for helping mental health, but they don't actually change people's behavior. So what's the problem here? I don't think it's that these aren't designed well or thoughtfully. I think this is the classic HCI problem, where until we actually deploy something out in the real world, we don't know what's going to work. So what we need is software that we can put out in a way that we know we're going to have to redesign it after it's been deployed. So my vision for online learning software is that we should have systems that perpetually improve, just like real teachers. For example, if you think of an online problem, when someone gets an answer right or wrong, it gives them an explanation. But if you were teaching in person, you would never give the same explanation over and over again to every person. Naturally, you would give students different explanations every time you explained it. And what that would mean is that over time, you could learn whether simple or complex explanations are helpful. And also, you could learn to personalize. My different explanations work for people with low versus high levels of knowledge. So how do we make online software more like a real teacher, able to test out different options and see what's working for different people? To give you a concrete example of this and why we need it, Think about our Professor Joe, who's teaching statistics. He's giving his students problems, but they're just not learning. They don't really get the concept. How do I improve the problems I give students? Or think of Samantha, clinical psychologist, where she's trying to help patients learn to deal with depression. So what she wants to do is give them scenarios, like help them reflect on problems they're having at work and think through how best to manage them. How could I, Samantha or Joe, enhance the software that they're using? More like one of these intelligent self-improving systems. So my approach to this is online experimentation. How many of you have heard of A/B testing? If you haven't heard of A/B testing. So basically, it's the term used in industry for taking different versions of websites or apps and seeing which ones users like. And so companies like Google and Facebook are really into this method as a way to improve products. And you can get thousands of people and test out what's working and then give the best to everyone. But actually, randomized experiments, which is the term we often use in science, have a much longer history in scientific areas, whether it's psychology lab experiments, experiments in education like classes, or medical trials. Maybe obstacles and challenges to trying to do these online experiments in a way that we can actually enhance learning. Your intuitions about what's a good lesson or will help people are often unreliable. I found that it's not until I run an experiment I know what's actually going to have an effect. It's also often not clear how do you even measure learning. And finally, even if you figure out what's having an effect, how do you then translate that into actually improving outcomes? So here's one approach that I take. It's to reimagine online experiments to be more collaborative, dynamic, and personalized. So my approach to HCI then is whenever someone gives me a piece of software, whether it's an online problem or lesson, I think of how to design a randomized experiment, just like the way you've been learning recently about experimental design. And to decide what conditions, what I'm going to experiment on, is it explanations in our lesson, or is it motivational messages? I draw my PhD in cognitive science. And so there in cognitive science, we write papers that really have to focus on how do we actually measure learning? How do we measure behavior? But that's not the whole story. You also have to work with instructional designers, people who have education experience out in the real world. If we run an experiment and get data, we still want to actually use that to help people. So in an ideal situation, we dynamically analyze experiments so that even if we start out assigning people 50% to one explanation, 50% to a second, we'd analyze data in real time. So after the first 10 or 20 students, we might know, well, this is actually looks like it's helping. So maybe then you'd assign 60-40 or 80-20 to dynamically change your experiment based on the data you're analyzing. And that would be good because in the long run, it would lead to enhancement, where you could give one condition to everyone, or to personalization, where you might find, for example, that one kind of lesson is good for low knowledge students, and another lesson is good for high knowledge students. How do we actually do this dynamic analysis? So that's where I and other people like me draw on work for my PhD in Bayesian statistics and machine learning. So I used to apply that to model cognition and psychology, but now I use it to build technologies that will analyze data from experiments in real time and provide the best conditions or personalized conditions to future learners. Now, even if we did all this, to get constant improvement, we also need to have systems that keep adding conditions. They never stop experimenting. And through that, I draw on work from HCI in crowdsourcing, where users or teachers can provide new ideas, and human computation. To enable all this, to go beyond simple A/B testing to these kind of collaborative, dynamic, personalized experiments, I developed a software requirement specification, which I call ADAPCOMP or MOOClets. It says that if you implement an A/B test instead of a MOOClet or ADAPCOMP, that just guarantees that you've got data structures and APIs so that you can do collaborative experimentation. You can do dynamic updating, and you can use machine learning in real time to personalize. So to give you an overview of the presentation, I started this vision: how do we make any online lesson or problem a perpetually improving system, like a real teacher? And I've said one approach that could be used, which is to reimagine experimentation to be collaborative, dynamic, and personalized. I'll now give you 2 examples of experiments out in the real world that enhance motivation of people learning in Khan Academy and show that if we design prompts for people to reflect, it can help them learn. Then I'll give an example of dynamic experimentation, where the adaptive explanation improvement system crowdsources explanations from learners to figure out which explanations learners find helpful and provide the best. This helps learning just as much as explanations from an instructor. Finally, I'll close with one example of how we can use experiments to discover how to personalize. And then I'll turn to future directions, because all of this work I see is just the foundation for future work by a range of people on how we can actually use experiments to bridge designers, social behavioral scientists, and machine learning researchers, and how we can actually push into other domains, like enhancing mental and physical health, by helping people learn how to change habits and behavior. So to start on the first part, so 2 experiments about enhancing motivation and reflection. These are experiments I looked at in the context of math problems, where I'm trying to understand how can we design motivational messages that get people to solve more problems, and could we design prompts to ask people to reflect, ask students to explain their reasoning in a way that enhances learning. And this is work that was funded by a National Science Foundation grant, where we were basically funded to bring experiments out of the lab into a real-world setting. So the first study, what I collaborated with Khan Academy. How many of you know Khan Academy? How many of you have never heard of it? You're all again, you're in university, so you don't need all these free online resources. So Khan Academy is a platform that provides free online problems and videos. And so I collaborated with them. We run some experiments to enhance learning. And what they were most interested in was trying to motivate people to solve more problems. And especially, they asked, what's the simplest change you can make, technically, with respect to software, that can give us the biggest bang for our buck? And so I drew this psychological theory to design some messages. And so this is a growth mindset message to be added to Khan Academy. Remember, the more you practice, the smarter you become. And so this is based on research from psychology, that if people believe intelligence is malleable, that you can get smarter through effort, it motivates them. If they believe intelligence is fixed, then every mistake is a sign that you're not good enough. So we wanted to teach people that intelligence was malleable, because then they would actually work harder and push through mistakes. So in our randomized experiment, maybe actually I'll ask a question. How many of you remember what's essential to, what does every randomized experiment have to have? So it has to have 2 conditions, because we're randomizing people to alternatives. So you want to compare a growth mindset message to something else. Well, what is that something else? Well, one thing is what I call practice as usual. It's just the normal problems people get in Khan Academy. So what's the question we're asking here? How does adding this growth mindset message help people more than nothing at all? Now, how do we answer that question? Well, what we're going to do is we're going to look and see how many problems the students solve when they get a growth mindset message versus when they get nothing at all. And if people solve 5 problems from a growth versus 4 from nothing at all, then we can do a t-test and see what the difference might be. How many people feel like they understand a t-test 100%? Okay, 0%. 50. Okay. So here's at least one place where you can actually use the t-test. And I won't go into the details of how you do it. Now, we also included another condition. Growth mindset practice as usual. We included a positive message. Encouraging. Some of these problems are hard. Do your best. Do you see why? So this message is a lot like the growth mindset message. They're both positive, but this one doesn't tell people that they can get smarter through effort. It just tells them, it's hard, keep going. So what we're curious about is if the growth mindset, telling people they can actually get smarter through effort, makes a difference above and beyond just encouraging people. So what did we find? Who predicts that the growth mindset has no effect at all? The growth mindset message has no effect. Growth mindset message is better than practice as usual. Encouraging message has no effect. Encouraging message is better than practice as usual. So you're right. The growth mindset message led to a 1% increase in how many problems people attempted. So not a big effect, but it wasn't a big manipulation. Most people might never have read it. But what is the effect of the encouraging message? Actually, encouraging messages were no better than no message at all. There was no effect of showing the encouraging messages. Does anyone recognize this P? Who wants to explain what that P means? No brave soul. So basically, for this kind of data, we did a t-test. We had about 100,000, 50,000 people in the growth mindset condition, 50,000 in the practice as usual. And people might have solved 1 problem, 2 problems, 3, 20. So you compute the mean number of problems solved. It was something, if I remember, I don't remember, but let's say it was 7.2 in the growth mindset. And then the mean in the practice as usual. Let's say it's 6.4. And then you have to ask, well, are those means really far apart? Is 7.2 that different from 6.4? Well, that depends on something, right? What does that depend on? Who thinks it depends on the number of subjects? Who thinks it depends on the standard deviation? So it depends on the standard deviation or variability. So what the t-test we did is you compute, is a 7.2 for growth mindset very different from a 6.4 for practice as usual? Well, in this case, the standard deviation was small enough that it was. So we computed the t-statistic, and then we did the test. And what that p-value of less than 0.05 meant is that if there was no difference in reality between growth mindset and practice as usual, then you would expect that there was just a less than 5% chance of getting as big a difference as we found. Whereas when we compared the encouraging message against practice as usual, there was a difference in the means, but it was so small relative to the variation that it wasn't very unlikely that you would get that. You could well have gotten that by chance. Okay, so that's kind of just, do you guys see how that's one example of how this thing you learn in class is actually something I use every day? In fact, Khan Academy would not have believed me if I hadn't done a statistical test like this. So now I'll tell them next time they can come to you to get their t-test, right? So what's the consequence of this research? Well, even though it's a pretty small effect, because it's done out in the real world and because we had good statistics to back it up, Khan Academy then launched a You Can Learn Anything campaign where they send messages to 11 million learners, encouraging the idea that by cultivating the belief that you can learn anything, you could trying to explain to learners that if you put enough effort and energy, you can learn anything you want. Also, they held a similar competition inviting other researchers to do these kinds of experiments. So that's one example of an experiment in math problems where we showed that these motivational messages, growth mindset, could help learning. But that was still a small effect. What I want to know is, could I actually enhance the size of the learning gains by doing something that would more directly target people's thinking? So in this case, I looked at, could we design questions that would get people to reflect in a more effective way? And the key idea here is, by asking people questions, we can get them to help people help themselves. In the same way that sometimes we lecture to you to give you information, but other times you get assignments, and those actually help you construct knowledge. So in my dissertation in cognitive science, what I worked on was a theory of why is it that asking why helps people learn? So if you're solving a problem, Professor Lim says, well, why do you think that's the answer? that can actually help you construct knowledge. So, but how does that work? So the idea that I tested in my dissertation was that when you ask why, it actually forces you to think of what you're explaining as an instance of a pattern. So if you know that 2 times 3 is equal to 6, but then Professor Lim says, well, why is it 2 times 3 equal to 6? You can't just memorize. You have to think, well, why is it? Well, it's because multiplication has to do with repeated addition. So it helps you find a pattern or principle. And this then gives you a basis for generalizing. So I use this theory to try and design prompts that would help people to reflect. So in this study, which we ran with crowd workers, we gave them statistics problems. So people would see the problems, they'd attempt them, and then be told the correct answer. After seeing the correct answer, we then prompt them to reflect. In the explain condition, they were told, explain why this answer is correct. In the right thoughts condition, they were told, write any thoughts you have about this answer. And so that's actually very closely matched because they both involve verbalization. In fact, many people would expect that these would have the exact same effect. But the explain prompt is designed using this psychological theory, that prompting people to explain why helps you find patterns. Which of these would actually enhance learning? We gave people a pretest, so they got similar problems, but we didn't tell them the answer. We wanted to see, did they know how to solve these statistics problems? Then they would solve 6 of these problems, either being prompted to explain, they were randomized to that condition, or they were randomized to the right thoughts condition. And then we gave them a post-test. So we want to see, by explaining writing thoughts, did they actually increase their ability to solve these problems? So in the vertical axis, you can see accuracy increase from pre-test to post-test. So who predicts that right thoughts helped learning more than explaining? Who predicted that explaining helps learning more than right thoughts? You guys are just being nice to me. Maybe my theory wasn't actually that good. I just showed you several studies where there was no effect at all that I thought would be there. Okay, so writing thoughts does enhance learning. There's an increase from pre to post. But prompting people to explain significantly increased learning. And so what we found is that learners said that explaining really lets you understand the logic behind it. So you're more able to solve similar problems. Or talking out really helps. I'll try and use that strategy for other problems besides math. So explaining got people to reflect and identify the underlying principles. So they were able to understand the general rules behind statistics, revise the incorrect ideas that they had. So the key contributions of this work are by adding motivation messages based on psychological theory of growth mindset, we can actually get people to attempt more problems. And by using a theory of explanation, we're able to prompt people to reflect, to help themselves. A HCI perspective is basically a kind of human computation. We're not actually getting the system or an algorithm to give feedback. We're using psychological theory to design just the right question so that you can actually engage the machinery of people's minds so that they are able to generate the feedback themselves. So it's being able to sort of engage people to generate the knowledge that they need. But they might not have been able to do it if we didn't have the interface hook into their minds in just the right way. But this isn't really good enough, is it? I said that I wanted to kind of have experiments that would push towards self-improving systems. But these experiments just had a few conditions, and they didn't dynamically improve over time. How do we get to this kind of scenario where we keep adding conditions and we analyze the data in real time to help future people? For that, I'm going to look at a context where now I'm going to run experiments on which explanations we give people for how to solve problems to see which explanations will actually help people learn. So this is the Adaptive Explanation Improvement System, or AXIS. So the problem that I'm trying to solve here is that you all know you can attempt problems many times, but just being told the correct answer doesn't always help you. You don't know why it's correct. And so you can't use that knowledge to solve new problems. If someone like your professor explains to you, well, here's why it's correct, it's because it's using this chain rule. That can give you the knowledge you need. The problem here, if you look at many online courses, there aren't explanations. People don't have time to write them. On experiments and explanations, how are we going to get instructors who hardly have time to write one explanation to write 2 or 3? Do you have any ideas, if we're in an online course or an on-campus course and we want to get new explanations to give learners, where could we generate these from? Do we use artificial intelligence? Okay, here's a hint. How could we use the approach of my previous study to actually generate these explanations? Anyone want to suggest? Yeah? So we actually get students to provide them. So we're crowdsourcing from students as a byproduct of what they're doing. So that helps us keep adding new conditions. Every time a student explains, we get a new explanation to test out. But there's a problem. How do we know that those students' explanations are actually helpful for other people? They find it helpful because they're reflecting. It may not be useful for a new student. So how could we use experiments to solve that problem? How could we use experiments to find these good explanations? Yeah? Yeah. So test out these explanations and see what students actually find helpful. Exactly. And in particular, we could analyze that data in real time and then dynamically adapt what we show to future students. And so if you analyze this data with something like a t-test is normally used in a static way. Like on the Khan Academy study, I got a ton of data, I did a test, and I reported it. I said, hey, Khan Academy, look, there's an effect. I'm going to use methods from Bayesian statistics or Bayesian statistics, where I want to analyze that data in real time. Every single time someone gives me a rating as a student, I want to analyze it and update what happens to the next. So here's the actual workflow. Here's the sort of interaction people have with the system, Access. So as before, learners see a problem. They attempt it. They eventually get told the right answer. Now, after that, we give them an explanation for why the answer is correct. And that comes from our current pool, from our current experiment. Now, as someone mentioned, we need a way to measure the outcome, which explanations are helpful. And so what we did is we actually asked students to rate how helpful was the above information from your learning on a scale from 0, completely unhelpful, to 10, perfectly helpful. Then we told them to help you learn, explain in your own words why the answer is correct. So I hope you don't think we're tricking them. We showed in the previous study, it does help you learn to explain why your answer is correct. So it helps them reflect. But they're also helping us, right? Or they're helping their friend. Because if their explanation was longer than 50 characters, and they checked a box saying it would be helpful to someone else, then we added it to our pool. And so it became part of this experiment to give new students the explanations. So now we have to ask, how are we going to run this experiment in a dynamic way using Bayesian statistics? So the way I think about dynamic experimentation is using methods from reinforcement learning. So reinforcement learning is a subfield of machine learning and artificial intelligence, where they're interested in balancing exploration versus exploitation. I'm going to use a particular method called multi-arm bandits, and in particular Bayesian interpretation. If you Google multi-arm bandit, you'll see it pop up. But I can tell you, you've met them before. Every time you go on Facebook, I'm sure they're running multi-arm bandit algorithms to see, do you like the button here or there? Do you want this message or that? And I know because I've gone to the Facebook data science team. They're like very big on this. They publish papers on it all the time. And it's actually good for you, right? Because the key idea here is that they're trying to balance. Here's how I formulate multi-arm bandits, right? The idea is a multi-arm bandit as a problem means that there's a set of actions. In this case, there's a set of explanations. And the goal of this computational problem is to say, let's choose these actions to maximize reward. In this case, we want to choose explanations that have the highest rating. We want to give students the most highly rated explanations. And so the way it fits in reinforcement learning is that exploration means let's try all the explanations to see what's rated highly. Exploitation means I tried some explanations out and I saw this one looks like it's rated higher than that. Let me exploit that knowledge by giving everyone the highly rated explanation. So that's why Facebook is doing it. Because they don't just want to run experiments for fun. They want to run experiments to figure out what's working, but they don't want to give the interface that people don't like a lot any longer than they have to. As soon as they see that an interface change is popular, they want to roll it out really quickly. So that's why they use these multi-arm bandit algorithms. And I use them in my case because I don't want to give students low-rated explanations. I want to quickly figure out what's working. So the other part of a multi-arm bandit is the policy. At any given point in time, for student 1 or 10 or 20, what explanation should you assign to them? And so the policy that I use uses randomized probability matching. It's an algorithm called Thompson sampling that's based on Bayesian inference. So I'll slow down a bit here. The kind of key idea behind this algorithm, let's actually know what, there's a very funny name I've seen online. It's called Bayesian bandits. So if you Google Bayesian bandits, you're going to see it right away. So it's multi-arm bandits from a Bayesian perspective. I think that's a good summary of what Thompson sampling is. But here's the key idea. What's the policy, how you decide what explanation to give someone, is basically to say there's a probability distribution. There's a 50% of giving someone explanation 1, 65 explanation 2, 20 explanation 3. Well, where do those numbers come from? Basically, we calculate the probability that that's the highest rated explanation. So what's the probability that explanation 1 is the highest rated? Someone want to answer? Who says it's 15%? Who says it's 65? Okay, so I realized I actually didn't explain that well. So this algorithm basically says that the way you decide what explanation to give someone next is to calculate the probability that that's the highest rated explanation. So what I'm showing you in this graph is one example of a policy. So what that policy said is, right now, I think the probability of explanation 1 being the best is 15%. I think that probability of explanation 2 being the best is 65%. So it basically calculates the probability of each explanation being the highest rated, and then it uses those probabilities to give the next student the explanations. So maybe it actually might be worth saying a bit more about where those come from. What do you think, Brian? Like I should say a bit more about where those might come from? Sure. Okay, so actually, let me give you a concrete example on that. Okay, so basically, in computer policy, we need a set of parameters or model. And in particular, I'm just going to say what it is. You can Google it later. But we use a beta distribution. So the idea is the probability of an explanation being rated helpful follows a prior distribution. And that prior distribution is a beta distribution. In fact, we use a beta distribution with parameters 19 and 1. And that corresponded to basically saying, before we show an explanation to any students, let's pretend like it got a rating of 9 and a rating of 10. Now, to figure out which explanations are good, we're going to actually use a likelihood function, which is we assume that people's ratings of explanations are drawn from a binomial distribution, where there are 10 samples in the binomial distribution. And the probability of a success is the probability drawn from the beta distribution. So the probability of success in this binomial is the probability of an explanation being rated as helpful. And then what we do is we use Bayesian inference so that every time we get a rating from someone, we actually update our estimates for these models. So we update our prior over the beta to get a posterior distribution. So to give you an example, let's say someone rated an explanation an 8. That's as if they gave it 8 thumbs up and 2 thumbs down. And so that would then increase our estimate of how highly rated that explanation is. Every time we get an observation from participants, and over time, we're constantly updating. So let me show you one example of what this looked like. So when we deployed Access, we deployed it with 150 people. This is a sample size I chose because it's about the size of a large undergrad course, offering a high school course a couple times. Because we're trying to get methods for crowdsourcing explanations that would actually work with samples that most teachers have, not just people running large online experiments. So at the beginning, students are interacting with the system, Access. They're sort of explaining, they're getting explanations. At the beginning, there's no explanations at all. They just solve problems. But over time, there might be one explanation, and then 100% of people are getting it. If they get 2 explanations, what's the probability of people getting each one? Well, just like a classic randomized experiment, at the beginning, it's 50-50, because we don't know which one's better. Our prior belief is that we have no idea. But as students rating it, and we see what's rated more or less highly, that probability changes. So it might be 20-80 if we think the one's rated higher than another. But then another explanation might get added. And so what happens is that over time, we're constantly updating this probability distribution, analyzing data, and computing what's the probability that each explanation is the highest rated. And then we use that probability to give the explanations to future students. And so what you end up with at the end of these 150 people is a policy that is a probability distribution over explanations. Here's one simple policy. It could say, let's give one explanation that we think is highest rated to 100% of students. But that's not actually what we got. To do that, you have to have really high statistical confidence that that's the best. You have to do a ton of t-tests. Instead, what you really end up with is a probability distribution that gives you a few that have decent rating, 18%, 1822, and then a bunch that have low. So explanations that have low ratings end up with low probability being presented, and then gradually phased out, get raised up. I just want to run you through that whole thing, but I know that was a lot of new concepts, and I'm guessing 5% of you would have understood like half of that. That's fine. The whole point of learning is like you get to revisit concepts. So let me actually try and explain that again. And Brian, let me know if you have any suggestions how I should kind of frame that.
Yeah, you want to introduce some of the probability terms to
Gotcha. And probability terms like Bayesian or theta. Okay, great. Okay, gotcha. Great. Okay, let me think. Okay, so if I draw, I'm not sure if you guys won't already see something if I draw it, will you?
Yeah.
Okay. Okay, so I think that's okay. You can ignore a lot of that math, to be honest, and don't feel bad. Like when I present this like to social scientists, 80% of them are like, okay, just give me the cliff notes, right? Because you don't know everything that's going on. Any new concept, you're not going to. But basically, okay, let's pretend you had 2 explanations, right? So let's say you had a simple one. Actually, let's okay. So let's say I say, I'm going to put you in charge of running this experiment. You're going to run an experiment. You're going to give a simple or complex explanation to every single person here. And at every point in time, I'm going to tell you, listen, you decide the probability that I should give someone an explanation. So let's say we start on this end, right? So you guys have to decide, we can give him a simple explanation or complex, and then ask him to rate how helpful it was from 0 to 10. So what probability should we use? Like right now, you might think, well, if I think a simple is better than a complex, maybe I should give him the simple. I should say, I'm going to give him the simple 80% of the time and the complex 20%. Because I think it's better, so I should give him a higher chance of getting the good thing. On the other hand, if you actually don't have any idea, if you think that your prior belief before you've seen any data is that they're equally good, then what probability should it be assigning with? Should it be less than 50? Should it be more than 50? Should it be 50%? Okay, so I would say, you could say, well, let's give it to 50%. And so the idea is that before you've seen any data, you don't know which one is better. So if I say, this is basically the whole idea behind Bayesian statistics. Before you see any data, we want to know how uncertain are you about what's true. So you have one hypothesis, which is the simple explanation is the highest rated. You have another hypothesis, which is the complex explanation is the highest rated. And you don't actually know what's true. That's why you have to collect data. You have to actually discover in the world what's highest rated. And you're going to discover it by giving everyone these explanations and collecting data. But before you've given it to him, you just have no idea. So what I would say is your prior belief is that there's a 50% chance this is the highest rated explanation, and that there's a 50% chance this is the highest rated. So now let's actually say that we give him that explanation, and that he gives it an 8. Now, what is the probability? How does that change your judgment of how good the explanation is? So you saw no data at all, right? And at first you were 50-50. But now you've seen some data. Simple explanation got an 8. Now let's say you give it to the second person, and he rates this one a 9. 8, 9. How does that change your estimate of how likely it is that this is the highest rated? So if he rated this an 8 and he rated that a 9, do you think this has a higher probability of being higher rated than this one? So put up your right hand if you think that's a higher probability of being rated. Put up your left hand if you think that's a lower probability of being rated. Now, you could also say, well, maybe it doesn't. Maybe the better question to ask is, how much higher is it? So suppose someone was to say, well, you gave that a 9, I gave that an 8. So I think there's a 100% probability that that's the best explanation, and I think there's a 0. Would you agree with that logic? Who would agree with that logic? That because I saw 1 8 and 1 9, there's a 100% chance of this being higher rated by everyone else in the room. So who agrees with logic? Who disagrees? Okay, but why do you disagree? Let me give an argument for why this person's right. Listen, I don't know anything at all, but that was higher rated. I'm sure everyone else in the room is just like him. So I'm sure they're all going to give that a 9 as well. What's wrong with that logic? Well, suppose we actually went to him again and said, hey, here are the explanations. Is he definitely going to give a 9 again? I mean, now on a different day, a different time, you might give it something else. Now you might actually give it a 7. So this is basically the idea that we're trying to figure out what's higher rated, right? But we're just sampling observations from a population. The population is everyone in this room, right? We've just sampled one observation. So we can't be totally sure that that's actually telling us the truth. On the other hand, we did get some data, so we should update our beliefs to some extent. And so the key idea of Bayesian statistics is that you start with some prior beliefs, like I have no idea what's better. Your prior beliefs are that these are equally likely to be good. And every time you get data, you actually update your beliefs. So then you go from thinking there's a 50% chance he's each right to thinking there's some other probability. So you guys just make up numbers. What's the probability what probability should we put here after seeing one of these, 8 versus 9? I'm just going to point at someone and just throw out a number. Okay, number. What's the probability if I saw that he rated a 9, he rated an 8? What's the probability this explanation is actually higher rated? You can make it up. I couldn't calculate it myself. 40, okay. What about you? if someone rated this an 8 and someone rated that a 9, what's the probability that this is actually truly going to be rated higher by everyone else? You can just make it up, really. Okay, how about you? You want to give a rating? What's the probability that's higher? 60, okay. So what you're seeing here is that we're not really sure. And that's why we actually have to keep collecting data. So it could be 50, it could be 55, it could be 60, it could be 40. So we have to keep collecting data. So now we go to the third person and we ask them, well, here's an explanation. How helpful was it for you for learning? Then this person might give a 6. Then we go to someone else and we ask, well, how helpful was this for your learning? They might give it a 5. And so over time, we keep actually getting more and more data. And eventually, we're going to get a better and better estimate of how likely it is that this really is higher rated. And so that's one of the kind of key ideas behind Bayesian statistics, is that you want to analyze your data every single time you get an observation. And so you take what you believe before you saw any data. Like that there's equal probability of these expressions being higher rated. And then every time you get some evidence, like someone giving it a high rating versus giving it a low, you update your estimate of how likely it is that it's actually going to be highly rated by everyone. Any questions about that? So when do you normally break? Oh yeah, sure.
Does this mean that if your prior belief is like a uniform distribution, then is the frequentist approach same as the Bayesian?
That's true for certain choices, yeah. You can choose a prior that will basically give you very equivalent results as doing a frequentist test, yeah. It's not necessarily uniform, it could be uninformative, or it could be something else, but there's always a prior you can choose. It'll often give you similar results. Well, often there's a prior you can choose. Yeah. So maybe how about, how often do you break normally?
5 minutes.
Okay, sure. Yeah, so how about you just absorbed a bunch of heavy things. So why don't you take a break for 5 minutes, and then I'm actually just going to go through this exact thing again so you guys can see it, and then we go on with the rest of the talk. Oh, you have a question?
I was just curious with how would you define the value function?
So in this case, function, you're saying, how do we actually model the quality of an explanation? In this case, we're saying the quality of an explanation is the rating of how helpful it is. Okay. So there are other ways you could do it, but at least in this case, we decided it's how highly someone rates an explanation. That's our value function. And technically, we're using this binomial distribution. Okay, so maybe we take a break for 5 minutes. Are you guys ready to start back? Okay, so I'm just trying to make it short since you just absorbed a ton of math. And don't worry if you don't get all those concepts, that's totally normal. I would say if you want to learn a new math concept, it could take like 8 or 10 tries. That's actually quite normal. But hopefully at least put something in the back of your mind. So when you hear someone talk about it one day, like Bayesian statistics, bandits, you'll have some context. So just to remind you, I was saying, so there's a system adaptive expectation improvement that's going to crowdsource expectations from learners. And basically, because we give learners expectations and have them rate them, and then we actually prompt them to explain their own words. And based on the expectation they write, we can pass that to the future student. And so this is the technical part we went over in some detail, but the high-level view is we want to model this problem of experimenting dynamically as a multi-arm bandit. And what a multi-arm bandit is saying there's a set of actions I want to take. Like, I want to figure out which explanation should I give people. And so I want to find the explanations that are highest rated, that people give a 0 to 10 rating. I want to find whichever explanations are highest. And so multi-arm bandit has a policy. At any given point in time, which explanation do I give to someone? And so I said I use a randomized probability matching policy, where here's what you should think. It's randomized, but it's randomized with weights. And so it's a Bayesian approach where it says the probability of assigning someone to condition is actually the probability that that's the best. So when you see that explanation 1 has a 50% chance of being assigned, what that means is that there's a 50% chance that that's the highest rated explanation based on all the data that I've seen so far. And just technically, the model we use is a beta distribution, where we say the probability of explanation being rated as helpful follows a beta distribution. And the priors we used were 19 and 1, which is as if saying, before you see any data, let's just assume that each explanation was rated a 9 and a 10. Then we actually see data, and so we're assuming that ratings followed by normal distribution, where there are 10 samples, and the probability of a success is actually coming from the beta distribution. So what that means is that every time someone gives a rating of 8, it's as if they give 8 thumbs up and 2 thumbs down. And so that's where we use Bayesian inference. So every time someone gives a rating, we actually update our estimate of how highly rated each explanation is. And so what that means is when we actually deploy this with students, so we gave this to 150 people online, at the beginning, there are no explanations, but over time, they keep on adding explanations in. And so the probability of assigning people to explanations is actually being updated so that the highly rated explanations are presented more frequently. And what we end up with is a probability distribution over explanations. So it's not the case that we know one is best. It's actually the case that for each of the explanations, there's a probability of assigning it to people. And that probability is higher if the explanation was highly rated and lower if it was got a low rating. Does that make a bit of sense to you? So now what we did is we deployed this machine learning algorithm to say, well, let's find which explanations are highly rated. But you might then say, well, being highly rated doesn't mean they actually help learning. So then I did a separate experiment to test whether these explanations that came out of the system would actually help learning. And so in one condition, we just gave people normal problems. In the other condition, we gave them problems with the explanations from Axis. In the third, we gave them the problems with what's called filtered explanations. So these are explanations that have low probability, less than 5% probability of being assigned by Axis. In other words, it had a sufficiently low rating that Axis doesn't think it's a good explanation. And finally, as a gold standard, we also gave some students explanations that were written by the instructor. And so just like the previous study, to see if these impacted learning, we actually gave a pre to post test. So we gave a pre-test where we got people to solve problems. Then we gave them problems that either had no explanation, they had the Axis explanation, and so on. Then we gave a post test. So what you see in the accuracy increase is how much did people's accuracy increase from the pre-problems to the post. So what do you predict? So what we find is that Axis explanations lead to significantly more learning than no explanations at all. So even though they were crowdsourced from students, the Axis system was able to select highly rated explanations that were good enough that giving these to a new batch of students actually helped learning. But you might be skeptical, right, and not really believe in that. You might say, well, of course an explanation helps. It's an explanation versus nothing at all. So that's why we had these filtered explanations. So these are explanations that Axis gave low probability to. And what you can see is that getting one of these explanations doesn't help learning any more than getting nothing at all. It's like you got nothing. So it's not the case that any explanation helps. Here's the gold standard, the instructor's explanations. So for you to use this system, how good would the explanations have to be compared to explanations from a real instructor? Is it half as good? 75% as good? Actually, there isn't a significant difference between these. So when we do a t-test comparing these, we find that there's no evidence that Axis explanations are any different in how much they help learning from a real instructors. And the instructor even admitted that they thought the Axis explanations were comparable to their own. So the kind of key takeaway of this kind of research is showing that we actually can do crowdsourcing from people who are doing it just to help themselves. And here's an example where we're actually using dynamic experiments, using Bayesian statistics to put data into practice to help people. So this is just a first step. There are many limitations and future ways you can improve this research. One could actually be to involve teacher input. So perhaps having teachers give their ratings of explanations could allow us to take out explanations that students think are good but actually have the wrong idea. You could also apply this to many broader applications, areas like health behavior change. You can think that maybe we could apply this dynamic experimentation to different messages or explanations that we give people for why some things are healthy or not. Or ideas that you give people for how to quit smoking. Another context is forums for community question answering, where if someone is watching a video and you ask them, well, a question like, what's the key assumption on IEBs? They might write an answer. But then you could actually take this and put it on a community question answering forum or discussion forum, so that when someone else actually asks this question, you can actually crowdsource answers to it, and then test which ones are helpful. So having summed up that kind of key idea, I just want to give one quick example of how you could use experiments to discover how to personalize. This was a study being run at Harvard where an instructor wanted to send emails to people and find out why were they dropping out of the course. And so the goal here was to maximize how many people actually responded to the email, much like probably professors wish you guys would respond to your emails. So in this experiment, we compared an introductory message. It was basically asking people why to take a short survey, and there was a brief message versus a message that mentioned that they've been absent. It's been a while since you logged into the course, so we're eager to learn about your experience. So what these results show is on the vertical axis, response rate. What proportion of people actually respond to the email? So what do you predict? What's the effect of the brief message? What's the effect of the one mentioning people are absent? Actually, overall, it looks like there's no significant difference. When you do a t-test on this, there's no evidence that there's actually any difference. So at this point, you could say, well, let's just give up and go home. There's no effect, right? Let's try something else. On the other hand, what if actually the messages were working differently for different people? So here's data now broken up by low and high activity. So low activity people actually were those who had been active for 0 or 1 day so far. And so they actually were more likely to respond to the brief message, perhaps because they weren't as engaged, but they were likely to read something short. On the other hand, people who've been active for 2 or more days, high activity people, were more likely to respond to the mention absence message. Maybe because they wanted to justify why they'd been out of not attending recently. So you can see that even if something's on average not looking effective, it might be that it's working differently for different people. And what this means is that if we actually thought, well, what if we actually try to optimize by personalizing? Let's give future learners the brief message if they're low activity, and the mention absence message if they're high activity. This could actually increase response rates by up to 14%. So you can actually optimize by personalizing what you send to people. So can you see how you might actually turn any A/B test, any experiment, into this kind of engine for personalizing? Whether it's Facebook apps, whether it's health, whether it's actually any website you build. You might build different versions, not just to see what's better, but what's better for who. So I'll turn to the future direction, since I think what I presented today is just showing examples of a whole range of work that can be done in the future. So one idea here is thinking about how you bridge designers, social behavioral scientists, and machine learning. And the other is actually generalizing this approach to settings like enhancing mental and physical health by learning how to change habits and behavior. So I see experiments as almost like a common language. It's very simple. Let's try a lesson A or lesson B. Let's send motivational email 1, 2, or 3. And they help bridge designers who want to solve practical things like get people to respond to emails, or people who make apps and want to figure out what messages motivate people to quit smoking, with social behavioral scientists who normally actually want to understand, well, how do people think? How do people reason? And they normally do studies in labs. And finally, it connects to statistics and machine learning researchers, because they're the ones who build those algorithms, those dynamic algorithms that actually figure out what's working for who and deploy that data in real time. So one future direction that I'm working on is actually this Arab that software requirement specification. So everything I presented, this dynamic experimentation, if you go and try and do A/B testing just out in the wild, most platforms just don't support that. At least when I've worked with platforms like Khan Academy to edX, you can't just turn an A/B test into dynamic experimentation. You can't just add new conditions. But what the specification has been designed, and we have mentioned a Python Django web app, is basically a backend that guarantees that you can run your simple A/B tests. But at any point in time, you could switch to adding new conditions. Or you can plug in machine learning algorithms via API so they can analyze data and personalize. Another direction is thinking about how do we co-create experiments between designers and scientists. So in on-campus courses, I built an app that's worked. At Harvard, I used it for Canvas, but here we're actually trying to plug into IVLE, where actually researchers and instructors will work together to run experiments. And in this case, then, instructor might design some explanations they think would help students, while a researcher would use psychological theory to design different ones. And so they can actually see which of these actually help people learn more. How can we actually take our ideas and differences of opinion and convert them to a research study? Also, we need now actually to, you could also easily apply this approach to product design. So one other project I'm working on is inside of Slack. I'm working with someone who's trying to develop a coaching app to try and help teams come together. And so we're thinking about how do you actually test which questions will get teams to give each other feedback in a useful way. And that's a very common methodology within startups. Now we need to actually balance practical impact against doing scientific research. So designers just want to give someone whatever's working well. Scientists actually want to figure out, they want to explore what's actually working. They want to be very confident in the conclusions they draw. That's why a lot of scientists are the ones who are using t-tests every day. And it's actually something we have to convince practitioners to do because they're not aware that that's the proper way to do it. So how do we actually balance giving people what looks best with actually discovering what's working? Well, that's exactly where this kind of dynamic analysis can come in. It may actually be a way to balance the concerns of a teacher who wants to give someone something that's good against a scientist who's actually trying to rigorously analyze data. One other direction is actually thinking about these dynamic experiments as test beds for different algorithms and models. So in statistics and machine learning, especially here in CS, there are many people whose research program actually revolves around coming up with algorithms for things like bandits, for reinforcement learning. They develop the algorithms that eventually Facebook and Google will plug into their systems to figure out what's working for who, and how do we actually automatically give that to everyone. But often they can't actually test these algorithms in the real world. And so using this kind of Moodle add-up comp, it actually provides an abstraction for reinforcement learning so that you can actually allow researchers to plug the algorithms in via API. And so the kind of key idea behind the Moodle engine is that it takes any interface, like an online course or Facebook web app, and says, oh, guys, do you mind I'm not talking? Hey, I'm actually hanging up here, which means I must be distracting people. Thanks a lot. So the key idea behind this Moodle engine is that you've got an interface, whether it's an online course, or in fact, it could be a web app on Facebook. And you take a component of it and you make it one of these MOOClets. And what that means is that you actually make an API call when it's being loaded that says, well, tell me what version to assign. And that can be passed out to a machine learning researcher's policy. Then separately to that, you have a way of adding conditions, this version set. And this is what allows you to kind of dynamically keep adding conditions. And it sort of abstracts out so that an instructor could focus on just designing the experiment and not have to worry about the data part. And then finally, they've got this learner data store. And this guarantees that you've actually got data available to be analyzed in real time, and it can be pulled in by API, by machine learning algorithms. And we've got links there to if you're interested in the code or might be interested in kind of seeing how this sort of thing works, or research of this kind, feel free to check it out. And this, I think, is really thinking about the intersection of HCI and machine learning. So how do you do interpretable machine learning, and how do you do interactive machine learning? So this kind of interacts with some of the things that people like Professor Lim work on, except that the interpretability and interactivity here is more actually on real-time machine learning, sort of reinforcement learning. So the kind of key idea here is that how do we actually ensure that these algorithms are interpretable? So if an algorithm is trying to figure out what's working, and it's changing what's presenting. Many designers are not clear what's happening. So is it the case that actually using a Bayesian approach that lets people look at computing the probabilities of it being helpful is useful? Are designers able to better map data that's being collected to understanding how that actually impacts what users will see? It also allows for interactive machine learning, where one direction I'm interested in is maybe actually letting a designer influence how much an algorithm should explore and test out many things, or exploit. As soon as something looks good, just give it to everyone. Another really interesting idea is, especially when you look at settings like personalization, here's where you never have enough data. If you want to discover what's working with different people, and everyone's different in many ways, it might be really interesting to think about how do you encode people's prior knowledge by Bayesian models, such as how do you encode people's knowledge about which emails might work for different subgroups of people? That's something where if you get someone's encoded ahead of time, the algorithm can more efficiently figure out how to personalize. The kind of key idea here is thinking how we bridge designers who are building products with scientists who are testing hypotheses about learning or behavior with actually machine learning researchers. And together, by bringing together these different sources of human computational intelligence, you can actually build intelligent systems. Now, you might wonder, is this method restricted to education? Well, actually, one thing I'm very interested in looking at, and that people could certainly apply these methods to, is mental and physical health. Well, you might think of habit and behavior change almost as a form of learning. So one thing I've looked at in the past has been, how do we actually enhance people's learning from people's management of depression or everyday people's stress by teaching them cognitive behavior therapy? How do you get people to learn these strategies in a way that they can actually apply it in everyday life? Another direction is actually thinking about how do we actually help people coach each other? So you're all students and you probably struggle with getting things done on time. So here we're kind of thinking about how do you build systems that will actually help students coach each other, give them suggestions for questions they ask each other to kind of work on things like getting assignments submitted, dealing with stress, making sure to set their goals clearly. And more generally, if you think of something like apps for smoking or health behavior change, smoking is a huge problem for many people. And it's a classic example of where you do something even though part of you doesn't really want to do it. Well, handling these kinds of addictions has actually been found to work well if you use the right strategy. So there are tons of apps there that help people eat healthy. You've probably seen things about logging your fitness, exercising more. But the surprising thing is that many of them just aren't effective. And really small differences in how you actually ask people questions or what messages you say can have a huge impact on behavior. Just like you saw earlier where a small difference in the motivational message on Khan Academy makes people work harder. Difference in how you ask people to explain why has a big effect on learning. And so in that kind of setting then, there's huge opportunity to think about A/B testing things like questions. How are you going to avoid smoking today? Or how would eating healthier make your family happy? And motivational messages like, what are you going to do when you get home today as a break? Next time you're stressed because of that deadline, what will you do to relieve it besides eating junk food? And here's an interesting setting where you're given apps, right? But you don't actually get to design those apps yourself. That's a lot of work. But what if actually when someone gives you an app for planning your day or figuring out how to eat healthy, you actually can say, here's a message I want you to send me. Tomorrow at 6 p.m., I want you to ask me, did I do what I told Jenny I was going to do? Did I accomplish my goal for walking up these steps? So you're actually telling the app what it's supposed to try out on you. And so this is actually a direction where by looping people in, we can actually design components of apps that are sort of crowdsourced from people. So people can actually personalize it to themselves. You can sell an app what motivation messages you want, what questions you want to be asked. And that actually might make it more personalized to you. But you can see how that's helpful for other people. Because if you come up with a question that you find useful to reflect, it might actually work for someone else. So we can actually, the same way we did with the explanation system, get crowdsourced from people, messages that work for them, and then put these into dynamic experiments that could work for other people. Because I think one kind of key idea that comes out of HCI work is that a lot of the problems that we think of as biological, like health, have biological problems like diabetes, obesity, and so on. But they might actually have psychological and technological solutions. If we can build apps or build systems or websites or resources that can actually help people change their behavior, change their habits, this can actually have a much bigger effect on outcomes like society's health, diabetes, eating healthy, than whether actually you give people drugs or not. So in conclusion, to wrap up everything, I started this vision of how do we build perpetually improving systems? Any online lesson or problem or website that keeps improving the way a real person would. And I outlined my approach of thinking about reimagining experimentation to be collaborative, dynamic, and personalized. I gave one example of experiments in online environments where growth mindset messages on Khan Academy increased the number of problems people would solve, and asking just the right questions for people to reflect helped them learn more from math problems. The adaptive exploration improvement system was able to crowdsource explanations from learners and use machine learning to dynamically experiment so that identified explanations that help learners as much as a real instructor. I give one example of how you can use experiments to discover how to personalize by sending emails that on average look no different, but actually work better for different people. So you could actually optimize responses by transforming an A/B test into a personalized system. But I think the real excitement of this work is in the future. How can we use this kind of approach to bring together designers, social behavioral scientists, and machine learning researchers? And how can we generalize it beyond settings like education to enhancing mental and physical health, or really any kind of product development out in the real world? All right, so thank you.
If you have any questions, feel free to come up to Professor Williams later. And as for the R workshop, that would be helpful for the assignment part 2. But you guys need to learn a little bit more stats first, so we'll postpone that to next week. And today, everyone can have early release and keep that assignment.
And if any of you are interested in this work or anymore, you can always Google me, Joseph J. Williams, and send me an email. Or if you know friends who are interested in getting software development experience, feel free to put them in touch. Thanks a lot.